So in chapter 10 and 11, we talked about how useful epoxides can be in carrying out certain functional group transformations and reactions that form new carbon-carbon bonds. One method of synthesizing an epoxide is to react an alkene with a peroxy acid. Peroxy acids have the general formula RCO3H, okay? It's also called a peracid, okay? Now, these reactions are a lot of times called epoxidation reactions, so because epoxides are formed. And you can see two such reactions here, right? 13.6 and 13.7. And the peroxy acid that we're using is called M-chloroperbenzoic acid. Now, it a lot of times is abbreviated Mcpba. And the peroxy acid part, what you're looking at here, is a lot of times these two oxygens, right? The bond between these oxygens. Now, here's the tricky thing about this particular reagent, is it can be shown as Mcpba. It can be shown like this, or it can be written like this. You have to recognize that those are synonyms of each other. Now, there's some advantages to synthesizing epoxides in this way. One of those advantages is the reaction conditions are relatively mild, okay? And many alkenes are commonly or easily synthesized. So we've got a good starting material and mild reaction conditions. Notice in this equation here that the stereochemical relationship between groups directly attached to the double bond is conserved in this reaction, okay? So if we're trans-but-2-ene here, then we end up with trans-but-2-ene oxide. So trans. If it was cis, it would also be cis. So let's look a little bit at the mechanism and why this happens. So when we look at this mechanism, and I thought I was going to draw this mechanism out, but I didn't. So I was all ready to do that. Follow along here. We have our double bond, and all we've done is we've taken that peroxy acid and written it on its side like this, okay? So there's the chlorine, the ring, the C double bond O, and there's an oxygen, a hydrogen. This is a hydrogen bond, okay? This is a concerted reaction, which means it all takes place in one step, okay? So here's what happens. These electrons come up and attack this oxygen. These electrons come down and attack that carbon. This is a very weak bond. That's why it makes it reactive. These electrons jump here to form a double bond. There's that double bond there. Those electrons jump up and grab that proton, okay? I don't love the way this arrow is shown. I feel like this arrow should come over here and grab the proton. That's just my personal opinion, right? Is it should come over here and grab that. You can show it either way, but we're not going to draw arrows out into space. So that's just something to be aware of. Now, this avoids for us a carbocation rearrangement. So no carbocations are formed. There's no rearrangement there. Now, because this epoxidation takes place in a single step, the stereochemical requirements apply that we just talked about. So, for example, the stereochemistry is conserved. So when we look at this, there's a trans relationship shown here where this is coming out here and this is going back. That's coming out, that's going back. And what you can see is that trans relationship is the same here. So the stereochemistry that's here is carried over to the stereochemistry here. Now, one of the things that we can do is, or one of the things that we can think of is that the Mcpba is a source of oxygen. So knowing that the peroxy acid donates an oxygen atom to the alkene, we think of the peroxy acid as a source of an uncharged oxygen atom. And with that really simple, this is so simplified, with that simplified picture, oxygen here, right, is very electrophilic. Right? Because it lacks an octet. Okay? And it also has a lone pair of electrons. Okay, so the curved arrow notation is identical. I want you to notice this because we're looking for patterns to the general mechanism that we saw in the last screencast. Okay, now this obviously opens up some new ways that we can incorporate this into synthesis. So I'd like for us to do a synthesis problem. When we look at the synthesis problem, it's a hair different than previous synthesis problems. It's giving you the reagents, but you have to identify what is A, B, and C here, okay? And so we need to think through each of these. So we're going to start at the beginning, and we're going to ask some questions about the first reaction. So in the first reaction, what happens to the OH group in the presence of a strong acid? That's what this is. We're going to come down here and we're going to say, hey, look, that's phosphoric acid. And I know that's a strong acid, right? That's how we're processing this. I know that this is heat, right? So we've got this functional group with a strong acid and heat. What's that product going to be, right? What are the various factors we need to think of? So when we think through this, a strong acid is going to protonate the OH to make it OH2+, which is a fabulous leaving group, right? And so that means that protonated alcohol can act as a substrate in an SN2, SN1, E2, E1 competition. So you have to use the information that we learned in the last semester about those competitions. The winning reaction here is E1 because the attacking species is weak. The leaving group is excellent. The solvent here is protic, and heat favors elimination over substitution. So the first step here for A, what we know, right, is that product would look like that. So you may need to go back and review some of your chapter 9 information, right? So for the second reaction, what type of functional group does A contain, right? Well, we've synthesized A. We know it's got a double bond. And so now we need to look at the reagent, right? We need to recognize that this reagent is a peroxy acid. That's the reagent. And so we need to know, also we need to recognize that this is dichloromethane. And that's a solvent, and we need to ignore that, right? Because that's just a solvent. So the main thing that's happening here is we have an alkene reacting with peroxy acid. We just saw that mechanism. So we know when that occurs, this is the product we're going to get. So this is B, okay? And so now we need to ask ourselves, all right, we have B, right? If you've got a peroxy acid, we need to come here and say, hey, look, this is a strong base, right? how is that gonna, how we need to go through and think about OH is a strong base, Na is just a spectator ion, so that's OH minus. We need to remember that OH minus is a nucleophile, and it can open the epoxide in an SN2 reaction. So this is an SN2 reaction, right? And so when we do this, we open that up, we end up with an OH here and an OH here. But we also need to remember the stereochemistry, okay? This stereochemistry with the OH is going to be trans. So the final answer with the trans stereochemistry is that's our C. That's our final C. So we have A, B, and C here. When you have problems like this, you just walk through it step by step by step. That trans stereochemistry occurs because the nucleophile attacks from the side of the ring opposite the epoxide oxygen. So because of that backside attack, that's what gives us, it's attacking from the opposite side. So if the OH is on one side of the ring, the attacking oxygen is going to be on the other side of the ring, if that makes sense. And if it doesn't, you can always, we can walk through that more in my office. So please, please, please ask. Okay. So this is a really great example of a new step-by-step synthesis where we've reviewed two of our older concepts, elimination and substitution reactions, and then we've also incorporated the new concept that we've just learned. Now, like carbenes and peroxyacids, molecular halogens like Cl2 and Br2 can react with an alkene to produce a three-membered ring. However, something that's different is that the three-membered ring produced from a molecular halogen is so unstable that it goes ahead and reacts further, okay? So, for example, when you have cyclohexene, when it's treated with molecular bromine, which is Br2, and tetrachloromethane, and so this is just our solvent, okay? This is also sometimes called carbon tetrachloride. It's honestly more often called carbon tetrachloride, just FYI. And it's just a solvent, a racemic mixture of trans 1,2-dibromocyclohexane is produced, and that's shown here, okay? And so another way to say this is that molecular bromine undergoes an anti-addition across the carbon-carbon double bond. That got really wild on me. Hold on. So I want you to write that down. Molecular bromine, which is Br2, undergoes anti-addition across a carbon-carbon double bond. Okay, so that's the addition it undergoes. Now, although an isolated bromine molecule is not a, doesn't have an electron poor atom, the bromine molecule becomes polarized as the electron-rich pi bond approaches it. You can see that here. So this is electron-rich. It's going to approach here. It kind of like forces all the electrons to this other bromine. And so this one becomes electron poor. So that means that Br2 becomes an electrophile. So, right? So it becomes an electrophile when approached by the pi bond, because that pi bond is really electron rich, and so it's going to force all those electrons to the other side. Now, we need to think about stereochemistry for just a second. When we look at the mechanism, right, and And when we think about the mechanism, we think about the stereochemistry that we observe. The mechanism doesn't take place through a carbocation intermediate, because if it did, we would get both syn and anti-addition. And what we find is, right, we just end up with an anti-addition. They're on different sides. And so what research has shown is that this proceeds through a Bromonium Ion Intermediate. So when we look at this, I'm going to try to draw this ring kind of flat, where this part of the ring is coming out towards you, and then this part of the cyclic ring is going back, and that's where the double bond is, okay? So we have bromine approaching, right? And these electrons go up and attack that bromine, and these electrons come down here to attack that carbon, okay, in a concerted step. That's an electrophilic addition. Then, again, I'm going to show this as kind of being flat, so this is coming out towards us, right? What happens here is we now have a bromine that's got two bonds, and so it's got a positive formal charge. This is our Bromonium Ion Intermediate. Okay, and what happens is another bromine comes in and attacks, and it can attack from either carbon. This is symmetric. Right, I might have it attack over here, and these electrons go up there. Now, because it attacks from the opposite side, or the backside attack of an SN2 reaction, what we find, right, is that there's one bromine down, and then one bromine up in this anti-addition, okay? And so notice there's no carbocation intermediate, so we don't have to worry about a rearrangement. So let's work a problem here. Let's do a problem. Predict the products of the reaction that's shown here. Do you expect the product mixture to be optically active? Why or why not? Okay. So here's the first thing that I like to do. I like to look at this and say, okay, what functional groups am I dealing with, right? And I see here, as I'm evaluating this, I say, okay, hey, look, I see a double bond right here, all right? So that's a functional group. And then I see an ether here, but I know that ethers are pretty unreactive, right? And so I'm going to come over here and really think about this double bond functional group. And I'm going to think, how does the Br2 react with that double bond functional group? I'm also going to recognize that this guy here is the solvent, right? So he doesn't play a part, and basically I can ignore him. So my two big players, the two things I'm really interested in here are the Br2 and how Br2 reacts with the alkene. Okay, that's what we're looking for. So one of the things that we know with this reaction is that Br2 undergoes an anti-addition across the double bond. So that's going to yield two products for us. One of the products, it's going to look like this. Notice we're not changing any of the other stereochemistry. We're just focused around the double bond, right? And then the other product, looks like that, okay? So here's some questions to ask ourselves, because we've done the first question, which is basically predict the products of the reaction shown here. Check that off. We need to make sure we answer the next two questions. Do you expect the product mixture to be optically active? So each product of the following of the molecules are chiral, okay? And so that means they're going to be optically active. So yes, we would expect this to be optically active. The reason we'd expect this to be optically active is because we haven't produced enantiomers. These aren't enantiomers of each other. We've produced diastereomers, right? And so these diastereomers are going to be optically active, okay? So that's, and when we talk about this, the reason they're not enantiomers is because this chiral center is different from this chiral center, and this chiral center is different from that chiral center, but that chiral center and that chiral center are the same. If these were enantiomers, these chiral centers would be different as well, okay? So these are diastereomers, they're optically active. Now, chlorine can, just like bromine, add to alkenes to produce vicinal dichloride. So there's an example shown here where we have trans-2-butene. It reacts with Cl2, and we get the anti-addition of Cl2. This proceeds similar to bromine through a chloronium ion intermediate. Okay. Now, molecular fluorine and iodine also react with alkenes, but we tend not to use these reactions in organic synthesis. Fluorine reacts explosively with alkenes. When I was in grad school, a professor told me they used to go to conferences and identify fluorine chemists because they were the ones that were missing fingers, right? So people have generally gotten away from fluorine chemistry because they like to keep their appendages. And the reaction with I2 is just really slow, so it tends to be really energetically unfavorable. So even though in theory both of those things can happen, in practice people don't really use them. So we're not going to focus on those. So for our idea, bromine and chlorine are the things that react. And bromine and chlorine have the exact same mechanism basically, right? So they follow that same pattern. Now, bromine and chlorine add to alkynes in the same way basically they add to alkenes. So for example, we have oct-1-ine here. It reacts with one equivalent. Notice there's one equivalent of Br2, and it gives us the E and Z isomers here. Now, if you react this with excess, then what we'll see is these will go through a second reaction, right? And end up with all single bonds, okay? So you really have to watch in problems whether it asks you for one equivalent or excess here, because it depends with triple bonds how far this reaction goes. Now, Br2 adds to the alkyne in both what we would consider a syn and anti-addition. That's why you get the E and the Z here. This means that the reaction proceeds through a carbocation-like intermediate instead of the bromonium ion intermediate. If it went through the bromonium, I said incorrectly, the bromonium ion, then it would be an anti-addition only, and we'd only get the E isomer. So when we look at this, right, what we find, if we look at kind of like why this happens, what we find is that when you have sp2 hybridized carbons here, this ring strain is too much to form. So we're not going to get the formation of that ion because these are the way these are hybridized and the highly strained ring, right? So that's just not what we're gonna see there. We can use these to synthesize halohydrins. A halohydrin is a molecule that has both an alcohol and a halogen on it. So for example, this is a bromohydrin. This is a chlorohydrin. How we do this is instead of carrying out the reaction in carbon tetrachloride, we switch the solvent to water. And if we switch the solvent to water, then we can form the bromohydrin or the chlorohydrin. The reactions for halohydrin formation are stereospecific. So these guys, these reactions are stereospecific, right? And notice, right, the OH group and the halogen add anti to each other. Right? The stereochemistry here is the same as the addition of the chlorine or bromine across a double bond. And so if we kind of look here, back to that kind of ring that's coming out here, right? And we have a Br and another Br here. Okay. The first step is going to, oh, and I forgot my double bond. There it goes. My first step is going to be an electrophilic addition, where these electrons are going to come up here and attack the bromine. These electrons are going to come down here and attack the carbon. We're going to form the same bromonium intermediate, right, where water comes in, it attacks here, and these electrons pop up there, okay? This is an SN2 reaction. We have a backside attack. Right? What you're going to notice and let me draw this way up here just so it's kind of out of the way, is because it's backside attack, it adds kind of on opposite sides, right? But now we have this OH plus that's been added because that water comes in and acts like our nucleophile. So then we're going to have a proton transfer where another water molecule comes in and steals that proton, and those electrons go on that oxygen. And now we have, I put it way up there, our Br. So there we go. We've added our OH and our Br. A few things to be aware of. We also get the enantiomer here. Okay, I just didn't draw it, plus enantiomer. So just be aware that this does come out to be a racemic mixture. Now, regiochemistry becomes an issue with halohydrin formation when the alkene reactant is not symmetric. Okay, so this is an unsymmetrical or non-symmetric molecule. The carbon atoms there are distinct. With the distinct carbon atoms, you can get two possible constitutional isomers, depending on which carbon atom ends up being bonded to the halogen, right? So this is a CH2, this is a CH, okay? What we find is that this ends up being our major product here, with this being our minor product. And so the question, of course, is, why is that the major product? Well, the answer is really in the mechanism. If we come here and we look at this mechanism, and now one of the things I do want you to get used to is reading mechanisms when they're written out. So when we look at this mechanism, these electrons attack here and these electrons go back here. And these electrons go back up on the bromine, right? When this undergoes electrophilic addition, this water here is going to come in and it's going to attack on this side of the ring. Now, I want you to notice how the book does this. It's showing a really big partial positive here and a smaller partial positive there. There's a greater partial positive charge on this carbon because, right, we have a benzylic carbon atom there, okay? So this comes in, that goes up, that attacks there, and we get the OH here, okay? A benzylic, so this is benzylic in this case, but understand a secondary carbon can also accommodate a positive charge, right? Better than over here, right? So the nucleophile, right, is going to be more attracted to things that are benzylic or secondary, right? Because it has a greater partial positive charge,